Okay, picture this. A massive oil spill. It's an environmental catastrophe on a scale that's almost impossible to wrap your head around, right? You see those images, that black stain just spreading and spreading across the ocean. So the big question is, how on earth do you even begin to tackle a problem that huge? Let's get into it.
Yeah, that's the absolute nightmare question facing emergency responders. I mean, we're talking millions of gallons of oil just out there in the open ocean. How do you start to clean that up? The sheer scale is just mind-boggling.
So your first thought, naturally, is to just get it out of the water. You picture boats with those long floating booms and skimmers trying to corral the slick and literally suck it off the surface. But when a spill covers hundreds, maybe thousands of square miles, those methods, well, they have some pretty serious limits.
And this analogy just hits the nail on the head. It really is like trying to catch smoke with a net. The oil spreads out, it gets incredibly thin, and it's constantly on the move with the wind and the currents. Now, don't get me wrong, mechanical recovery is absolutely vital, but when you're up against a truly massive slick, it's often just not enough. Responders need another play in their playbook.
And that other play, that other strategy, is very often a chemical one. We're talking about something called dispersants. And look, this isn't some brand new experimental tech. The whole idea of using chemicals to break up oil slicks, it's been around for decades. And it's evolved right alongside our understanding of how to handle these disasters.
In fact, the idea got its first big test way back in 1967 during the Torrey Canyon disaster. The first versions were, pretty crude stuff. But the science got better, and it got better fast, leading to way more effective formulas by the late 70s. And of course, their use came into super sharp focus for the whole world in 2010 during the Deepwater Horizon disaster in the Gulf of Mexico.
Okay, so how do these things actually work? Well, the absolute simplest way to think about it is this. It's like washing a greasy pan. You add one drop of dish soap, right? And what happens? Suddenly, that solid slick of grease just breaks apart into all these tiny little droplets that you can just wash away. Dispersants do the exact same thing, just, on an oceanic scale.
But instead of a little bottle of soap under your sink, we are talking about massive, industrial-sized containers and barrels, just like you see here. This isn't a small operation. These chemicals are deployed by the ton to try and tackle these enormous slicks.
All right, so let's get into the nitty-gritty science of what is actually happening when that chemical hits the oil. It all comes down to a really special kind of molecule.
The magic ingredient here is something called a surfactant. And the best way to think of it is as a molecule with a split personality. See, one end of it absolutely hates water and loves oil. That's the hydrophobic or water-fearing side. But the other end loves water and hates oil. That's the hydrophilic or water-loving side. This dual nature, well, that's the key to the whole thing. So here's how it plays out in 3 basic steps. First, you spray the dispersant onto the slick. Simple enough. Second, those little surfactant molecules get right to work. Their oil-loving ends latch onto the oil while their water-loving ends face outwards. This action literally tears the massive slick apart into countless tiny droplets. And finally, the ocean itself lends a hand. The wave energy mixes these droplets down into the water where microbes that are already there can get to work and, well, eat them.
So, what's the point of all this? What does it actually accomplish? Well, it achieves 3 really important things. For one, it keeps those little droplets from clumping back together and reforming a slick. It also stops that super sticky oil from coating everything in sight, like bird feathers or sensitive coastlines. And by creating all these tiny droplets, it massively increases the surface area for those hungry microbes, which basically supercharges the natural process of biodegradation.
Of course, knowing the science is one thing. Actually applying it effectively, in the middle of a chaotic, windswept ocean, that is a whole other challenge. And getting the dosage right is absolutely critical. The general rule of thumb they follow is a ratio of 1 to 20. So think about that. For every 20 gallons of oil you need to treat, you only apply 1 gallon of dispersant. It's a surprisingly powerful chemical mix.
So how do you get it on target? Well, responders have a few tools in the toolbox, and each one has its pros and cons. Planes are the fastest, right? They can cover huge continuous slicks in no time. Helicopters, they're a bit slower, but they're way more precise, which is perfect for targeting smaller, broken-up patches of oil. And then finally, you've got vessels right there on the water. They are the slowest of the bunch, but they're great for hitting thick patches and, really importantly, for monitoring to see if the dispersant is actually doing its job.
So far, this all sounds like a pretty great solution, doesn't it? But the reality is, it's way more complicated than that. Using dispersants isn't some simple, easy fix. It's a really difficult trade-off, and it comes with some significant consequences.
And to really understand the stakes of this trade-off, just look at this number. During the Deepwater Horizon disaster, almost 4,000 tons of dispersant were used. When you introduce that much chemical into a marine environment, it forces you to ask a very, very difficult question.
And this really is the heart of the whole debate. Are these chemicals actually helpful? Are they preventing a worse disaster? Or are they just swapping one catastrophe for another, more hidden one?
Let's break that trade-off down. On the one hand, yeah, you can treat huge slicks incredibly fast. You can potentially save entire coastlines and thousands of marine birds from getting coated in that thick black oil. But the downsides, they're significant. You're fundamentally changing the threat. You're taking it from the surface and you're spreading it throughout the entire water column, where it can affect a completely different set of organisms. And this quote just captures the dilemma perfectly. There is no perfect, harm-free option here. It's not on the table. Responders have to make a choice. Do you risk the coastlines, the marshes, and the birds from the oil on the surface? Or do you risk the fish, the coral, and all the other organisms living below the surface from the dispersed oil droplets? It's a choice between two very bad outcomes.
And because this choice is so incredibly difficult, the use of dispersants isn't some free-for-all. It is absolutely not a panic button that you just slam the second a spill happens. It is a highly, highly regulated and carefully controlled response tactic.
In fact, there is a very strict playbook that has to be followed. You have to be in water of a certain depth. We're talking at least 10 to 20 meters. You have to be a minimum distance from shore. You absolutely cannot use them anywhere near sensitive areas like coral reefs or marine parks, and you have to constantly monitor the application to make sure it's actually working effectively.
And listen, these aren't just suggestions. Applying dispersants while ignoring these regulations is illegal. It can lead to prosecution. The decision to use them carries an immense weight and a lot of legal responsibility.
Which brings us to this final, really challenging thought. Dispersants are not a magic wand. They're a powerful, controversial tool used in the most desperate of situations. They really represent a calculated risk. It's a conscious choice to trade one kind of environmental damage for another, all while hoping, praying you chose correctly. It forces all of us to ask, when you're faced with a disaster and there are no good options left, how do you choose the least bad one?